All right, everybody. Today we are going to begin talking about piecewise functions. This will be our last day of really kind of true new material. We will get another day to actually practice some of these skills. But today will be our last day of new material for this chapter as we begin to lead in and to start thinking about a test. So, piecewise functions. What our objective today is that you will be able to graph piecewise functions, find the domain and the range, and identify the value at a given point in a piecewise function. Our notes today are starting on slide 47 if you haven't found them already. So it says to recall. So first thing that we want you to recall is just how you graph a linear function. Now you've been doing this for a really long time. Remember, if I have a linear function, I can always start at my y-intercept, which would be at 0, 3 at that point. And then having a slope of a negative 1/2 means just go down 1 over 2. Down 1 over 2, down 1 over 2, up 1 back 2, up 1 back 2, up 1 back 2. Nice straight line. Hip, hip, hooray, you did it. We're done, right? That's how we graph a linear function. Now, to graph a quadratic function, it looks a little bit different. So first off, you can either make a table of values. Let's actually make a table of values. That might be the easiest way to think about this. So making a table of values, x and y, we would have negative 2, negative 1, 0, 1, 2. As we go through, if we plug in negative 2 squared would be a positive 4. Half of 4 would be just 2, and 2 take away 4 would leave us with a negative 2. Doing the same for negative 1, we're just going to repeat that process. So negative 1 squared would be a positive 1. Half of 1 would be 0.5. 0.5 take away 4 would give us a negative 3.5. Plugging in 0, 0 squared is 0, half of 0 is 0, 0 take away 4 would give us a negative 4, and then since it's symmetrical, we know that this will end up being 3.5 and 2, and we can just simply graph those points. I'm sorry, negative 2 here and negative 3.5. Now, when we come over there, negative 2, 2 would give us a point right here. 0, negative 4 would end up right there. Negative 1, 3.5 would be about here. We get a point here and points there. So looking at my parabola, it would look kind of something along the lines of this. And it's just important to recall those basic facts because with piecewise functions, we are going to end up doing a lot of graphing. Most of the graphing will be with lines, but some of it will be with those other parent functions and different things we've been talking about. So what is a piecewise function? A piecewise function is basically a function in which there's at least two different rules that determine what happens with that function, and each of those rules is in place at different times, right? So here we see the function f of x. It looks like this. Now in math, there are no functions that just straight up stop and turn like this one does. So we can make a function that stops and turns like that by making what we call a piecewise function. So this piecewise function, f of x, is the name of it. Kind of has two rules that it works by. The first rule is that negative 2x minus 6. So it is that whenever x is between negative 4 and negative 2. So whenever x is between negative 4 and negative 2, that rule is in place. So we can see that we have that negative slope. It would have had that intercept of a negative 6, but that is where that's coming from. The other half of our function, let's call it the green half, is going to reside by this rule 1/3 x minus 1, and that's in play when x is between negative 2 and 3. So when x is between negative 2 and 3, that half of the rule is going to tell us what our function does, right? So a piecewise, it's just made up of pieces, right? It's a piece from the first, that gold section, and then it's a piece from the green section. That's what a piecewise function ends up being. So moving on, so recall, graphing linear equations, slope-intercept form. Remember, ladies and gentlemen, when we have this, this is our y value, or our y-intercept. So over here, 0, 3 is where we would start. And then since we have a slope of 2, that just means go up 2 over 1, It's like a rise over a run, and then just reverse it. Down 2, back 1, down 2, back 1, down 2, back 1, down 2, back 1. Right? This is where we started so long ago, just as we were getting into algebra with how do we graph linear relationships. Now let's sit there and try to twist this idea up on you in the form of a piecewise function. So again, we're given a piecewise function that's going to have two parts. The first part will be right up here, and the second part will be right down here. Now, what we want to do is we really just actually want to start by just graphing each half of that function. So I'm actually going to graph the bottom half first. Recall that I could just sit there and add a 0 onto this, and that my function would be y is equal to 2x plus 0. So if I have 0 at the end, I know that will be my starting point. And then my slope being 2 would mean go up 2 over 1 each time. Of course, you can then follow that pattern backwards, and you would have a picture of what that line is doing. Now, for the line up above that, the 3 minus x, this one is unique for sure. If y is equal to 3 minus x, this one might be a little bit harder to graph in this form, so we do want to rewrite this maybe to say negative x plus 3. Those two things are the same, and then I could slide in that negative 1, right? So up here, I could have my negative 3, down 1 over 1 to get my pattern, and then I can go up 1, back 1 to get my other half. Nice straight line to connect all of that. Oh, I missed some of my points there. Let's get a straighter one. Like so. Now, for my piecewise function, when I actually graph this, neither of these lines really are going to continue on forever for us because they're only going to work in certain situations. So, for example, this top line here, 3x minus 1, that's our green line on our graph right now. This line only works if x is less than or equal to a negative, or I'm sorry, less than or equal to 1. So looking up here at our graph, as soon as, so this is what's working. But as soon as I pass 1, this part no longer is in effect. So we really want to come over there now and erase all of that extra stuff that doesn't actually count. If we were just strictly graphing that line and it wasn't a piecewise, that would count. Now, what happens to the right there, right? When x is greater than 1, then our blue line is going to take over. So as soon as we come down here, right? So this is all x is less than 1, less than 1, less than 1, less than 1. Now we're at 1. As soon as we are bigger than 1, the other line is going to take over. Now, you may think, well, then does this bottom part not matter? And you're absolutely correct, right? Because that is when x was less than 1, and that doesn't work for that blue line anyway. So coming up here, this would be the piecewise function f of x for us. Now, looking at this, we can still do our domain and range. Looking at our graph, we can see that our domain will be all real numbers. And then looking at our range, our smallest y value is 2, and it goes all the way up until infinity. So that's good. And then really the last part, this is what we do a lot with piecewise functions, is at some point we're going to ask you to evaluate them. So this basically says, if I were to plug 0 into this, what should I get? And thinking about that, plugging in 0, since 0 is really, this is an x value, and 0 is less than 1, then we need to plug it into this top portion of the function. We would only plug it into the bottom if it was bigger than 1. So 3 take away 0 would in fact give us 3. So the output there would be 3, and we can actually see that. This is that point, 0, 3 as well. F of 1. Now again, 1 is equal to 1, so we need to plug it into this top one again. 3 take away 1 would give us an output of 2. Last but not least, 2.5. That one we need to plug into the bottom one, since 2.5 is bigger than 1. So plugging in 2.5 into the blue function, we're going to have 2 times 2.5, which gives us a value of 5. So at 2.5, we are up here at 5. Great. So really, that's kind of what's going on with a piecewise function. The graph is half of it. The other half is actually, can you plug in and get the appropriate output values? So looking at another one, again, we have another function named f of x. It has two parts. It's going to have the blue part, and it's also going to have, how about this reddish part? So first thing I notice is that for the top part, f of x is equal to just 3. Now 3 is a constant, it doesn't change. And what we're really talking about are y values there. So if x is between -4 and a +3, our y value is always going to be equal to 3. So between -4 and a +3, our y value is always equal to just 3. Okay, that one was relatively easy. Notice how I used closed circles as well because of the fact both of these were greater than or equal to. So we want to include those endpoints there. Now, moving on from that, for the red function over there, this one again is a line. So if we wanted to graph that, y is equal to 2x minus 3. Minus 3 is our starting point, and then we are going to go up 2 over 1 each time. And then we want to follow that pattern down in reverse as well. Now, this function takes over whenever x is greater than 3. So when x is greater than 3 is when this function is going to take over. So we can see that that would only give us those points. So x being greater than 3, we can see our two parts of our function showing up together. So now to simply come over there and evaluate, if we're looking at f is equal to 3, we should be plugging that into our blue function because this is the one that accounts for when x is physically equal to 3. So if I plug in 3 into there, I know that my output should be 3. Now, really not much to plug in because my output's always 3 if x is between -4 and +3. Looking at the second part of that, f of 7. Since 7 is bigger than 3, I want to plug it into my red function. So 2 times 7 minus 3, this would give us 14 take away 3, which would be 11. So f of 7 would be 11. Now for our domain from this, it looks like we are going to have domain values from -4 all the way to +infinity. And that our range values are going to be from 3 all the way to infinity. Great job. Let's look at the next one. So this next one's going to have 3 parts to it. So we are going to have our red part, our blue part, and let's make a green part as well. So looking at this one, again, easiest way to start is really just to start by graphing what you can. So if I start on the red one, y is equal to 2x plus 1. I know that that means start here and have a slope of 2. So up 2 over 1 each time. And you really want to go back each direction with that as well. Now, I'm just going to kind of, I think, leave mine right there. I'm not going to connect any dots because I do know some of these dots are going to get erased anyway. Now, f of x is equal to a -2. So between -4 and +4, our y value is always going to be equal to a -2. And both of those were or equal to, so I will have the closed circles there. And then moving on from that, what I'm going to do, my last part of this now, is when I come over here and I look at that x minus 3, remember that that's like 1x minus 3 is equal to y. So looking at that, minus 3, 1x, you may hear my dog in the background with its chew toy right now, apologize for that, would give me a line coming through like so. So now, after this part, now we just got to sit there and get the appropriate parts at the same time. So for our red line here, our red line is only in play when x is less than 4. Well, x is or I'm sorry, less than -4. So -4 would sit right here. So our red line only works to the left of that line. So kind of have a bad graph here for it, but it is graphed accurately. So we are actually going to have the red line working from there to there. And this has to be an open circle right there because we did not have the or equal to. So at that point, any of the other red dots really can disappear because those will never come into play because something else will pick it up at that point. Now, for our green function there, our green function is in play whenever x is greater than a +4. So greater than a +4 would be right there. So our green function is going to start right here and head that way. And again, since it didn't have the equal to in the symbol, this needs to be an open circle for us. And any of those other dots in the middle don't actually end up mattering for us, so we can erase those, which would give us this graph of our piecewise function. Now, at this point, we need to identify what would be the output value at f of 2. So since 2 is between -4 and +4, this would give us an output value of -2. And at -1, if I wanted to check -1, again, -1 also is still in that same range right there. So the output value at -1 would still be a -2. For the domain of this function, when everything falls down, remember this will fill that hole, and all of this will kind of get accounted for as it falls down, and our domain will end up being all real numbers. As for your range, when you're thinking about your range, it looks like we are going to have some gaps here. So we will have hits going from here to here, and from here to here, and then we also have a hit here. So our range would be from -infinity to -6, union, 2, union, 1, comma, infinity. And that would be it. Let's take a look at another one here. So this one's about to get a little bit more complicated because we do have a quadratic in the problem. So as we look at this problem now, in order to get our graph, we'll save that graph maybe for a little bit later, but first let's just color code everything. So let's make this our green one. I'm going to make this our orange one. Get some fractions in there even. And I'm going to make this last one our blue one. So let's graph our lines first. The easiest one to me looks like the blue, so let's graph that. Remember, this would be 1x plus 3. So starting at our y-intercept of 3, up 1 over 1. And again, I'm just going to leave my dots here because I don't even want to think about... Actually, I mean, let's try to think about this. If this only works when x is greater than 3, that means all of these dots over here don't even matter for us. Right, so those we could cross off. Actually, I think we can cross that one off too. So this would be our only graph, and since it's not or equal to, this has to be just an open circle down here at the end. So I'll have my open circle happening right there. Now if we go look at the orange one in the middle, looks like our starting point would be at 3/2, which is also known as 1.5. And then from there, we go up 3 over 2. So up 1, 2, 3 over 2 would give us a point right there. And again, I'm just counting my boxes. Up 3 over 2 would give us a point kind of somewhere right about there. Down 3, 1, 2, 3, and back 2 would give us a point right about there. 1, 2, 3, back 2 would give us a point right about there. And I can kind of start to see that line coming through. Now, this line is really in effect from +1 to 3. So +1 to 3 means this line is really only just has a short little life here from 1 to 3. So maybe let's try to actually connect this for a minute to see where we're actually hitting. And if this is in effect from 1 to 3, then I know that over here, this part of the line won't actually matter. And similarly, I'm going to lose kind of this top part right up there. So again, I still have my first line, which is looking good. And then I have my orange line, which is coming through kind of right on that little bit there. Now, since I do have the or equal to there, I'm going to actually fill in this circle with orange right now, because the orange line is really what's picking that one up. And I do have an or equal to on the other side, so I will have an orange endpoint there. Last but not least is going to be our parabola here. Now, looking at that parabola, we could rewrite this to say that this will be a negative x squared plus 4. Remember that when you have a parabola, or like we were talking yesterday with parent functions, this is going to move your locator point up 4 units. I should do that in green. The negative is going to mean you are going to flip. And then for your parabola, we do know that we normally hit these points. So my graph will be kind of coming down like so and like so. But I'm going to stop because I know that's where I'm going to hit and my orange function will take over. So really here, this is the graph of this piecewise function, which is pretty intense. If you're struggling to graph the parabola, remember you can always just make a table of values here and literally just plug in. You know that your middle would have to happen at 0. So 0, 4 is what you would get there. If you were to plug in a 1, you would end up at a positive 3. And if you plugged in a negative 1, you would end up at a positive 3 as well, right? So you can just sketch points that way at the same point. Looking at your domain, everything gets hit, so we would say all real numbers. For your range, same thing, all real numbers. The last part, this really ends up being the part that gets used the most, is actually just evaluating. So if my input value is 3, that would tell us to use our orange function here. Plugging in 3 to that, we can do it one of two different ways. We can actually even just look at the graph. So if x was 3, my y value will end up being equal to 6, which is the same thing I would see if I actually plug that in. And we can even check that too, so let's check it. So if I had 3 halves times 3, and then plus 3 halves, 3 times 3 halves would be 9 halves plus 3 halves, which would be equal to 12 halves, which ends up being equal to 6. For the bottom there, if f is equal to 4, since 4 is bigger than 3, we need to use this bottom one. Plugging in 4 plus 3 gives us an answer of 7. Terrific, great job. Let's keep moving on. I think we got 2 more slides left, and then we are done with piecewise functions for the day. So looking at this first one, again, only 2 rules here, so that's a nice little change. We have f of x is just equal to 1 if x is less than 0. So less than 0, we're equal to 1. That, of course, will be an open circle right there. And then for the second part, we have our square root function over here, which we just saw yesterday in our parent function. So looking at our square root function, let's call that just our red one down there. Remember, when we do this, you can just make a table to graph these things more accurately. Our parent function values were 0, 1, 4, and 9. Those were the ones we could take square roots of. So we know we'll have a hit at 0, 0, 1, 1, 4, 2, and 9, 3. 9, 3 doesn't even fit on here. So here is my function coming through. And again, the closed circle goes with the square root one. So f of 0, right, if I go to 0, I'd have to plug it into this one. Taking the square root of 0 is just 0, so we get that. Since 5 is bigger, we would also have to use this bottom one. So our answer would really be the square root of 5, which you could get a decimal approximation for too. Punching that in on your calculator, second square root 5 would be 2.23. Which we kind of can actually see right here too, right? So if I had that value of 5, 2.23 would sit somewhere right about there. The last part of this problem is just asking us to look at our domain and range. It looks like we do have that open circle, but that would be filled by that circle below, so our domain will be all real numbers. And then for our range, it looks like our lowest y value will really be 0, and then it will always keep increasing. So 0 to infinity would be our range. Last problem, again, this is what's probably the most useful with piecewise function, is just to evaluate. So if I wanted to evaluate f of 2, I would have to find where 2 belongs. Since 2 is greater than 1, I need to use this bottom rule. So 2 take away 3 means that f of 2 take away 3 would be a minus 1. And f of negative 1 would be equal to negative 1, so we're actually having to use the middle rule. We're not less than negative 1, which means f of negative 1 would be just equal to negative 2, because anything in that interval is always equal to negative 2. And just like that, we are done, ladies and gentlemen. If you have any questions, please don't hesitate to reach out. Piecewise functions, not incredibly hard if you can graph lines fairly well. If you struggle with that, I imagine you're going to need a little bit of help, and please, again, reach out if you need it. Have a great day. Thanks for watching.